Unit 2, Hydraulic Modification. Hydraulic modification is the process of providing a drainage path in the site to remove the pore water from the soil. In coarse-grained soil, this can be achieved by lowering the water table, but in fine-grained soil, it needs long-term application of loads to dissipate the pore water from the soil. Objectives of hydraulic modification technique. The main objectives of hydraulic modification are to keep the subsoil dry for foundation works, to accelerate the consolidation settlement so as to reduce the post-construction settlement, to decrease the pore water pressure and increase the strength. There are various hydraulic modification techniques like preloading, vertical drains, sand drains, prefabricated drains, stone columns, vacuum methods, dewatering techniques, etc., out of which preloading technique is the most widely used technique to accelerate the consolidation process of clayey soil. In this process, a heavy load is placed on the ground, which is called surcharge. The heavy load is nothing but either soil or stones placed on the ground, which will act as a static pressure and accelerates the process of consolidation. Even the artificial pond created with geomembranes can be used as static load to accelerate the process of expulsion of water from the soil. Due to this acceleration in the consolidation process, the saturated soil will be subjected to settle before the construction, and the settlement after the construction will be less. This method can be used to dredged material also to improve the slope stability and bearing capacity of this dredged material. So the applications of preloading of soil is to reduce post-construction settlement, to reduce secondary compression for densification, and to improve the bearing capacity. Preloading is a very effective and economical ground modification technique for accelerating primary consolidation and compensating some secondary compression of soft compressible soils. Other techniques involving for accelerated consolidation of soil are vertical drains, sand drains, prefabricated vertical drains, vacuum consolidation, and high vacuum densification method. The first one is sand drains. Sand drains is a process of radial consolidation which increase the rate of drainage in the embankment by driving a casing into the embankment and making vertical boreholes. In this method, the boreholes are drilled to the desired depth, the drilling tools are removed, and the boreholes are filled with sand. These drains are installed in a triangular or square pattern. Here the drainage path is reduced and the pore water is collected in the sand drains. A sand blanket is placed above the ground so that the water collected in the sand drains will drain through this layer and it will be extracted. If the subsoil is highly compressible with high values of settlements expected, and if the construction has to be started early, the consolidation process can be accelerated by providing preloading along with sand drains. This surcharge placed on the soil further accelerates the process of consolidation. The next method is prefabricated drains. Prefabricated drains are another emerging technology for removing the pore water. Here a geofabric is used as a drainage path which will be inserted using an installation rig. A grid is marked on the site with the designed spacing. The rig is positioned at the grid point. An anchor is placed on drain end. The geofabric is attached to the mandrel and is inserted to the desired depth. The mandrel is withdrawn, leaving the fabric in soil. The fabric is cut above the level of drainage blanket. Here extra projection is taken to avoid burying under drainage blanket, that is a sand blanket, which will be placed after the installation of vertical drains. So this is a vertical drain installation sequence. Positioning the rig, penetrating the mandrel along with the prefabricated drain, leaving the mandrel in place and removing the mandrel, and finally cutting the drain material above ground level. Next method is vacuum consolidation. In this method, the soil to be treated is covered with an airtight membrane like geomembrane, and vacuum is created using a vacuum pump. This method can provide an equivalent preloading of about 4.5 meter high as compared with a conventional preload. The advantages with this method when compared with preloading are: there is no need of transporting and dumping surcharge on the soil, and it is also reduces the time of treatment. So this method can also be used at landfills to extract gas. This method can be more effective when combined with preloading technique. The preloading further enhances the consolidation process when compared with the conventional preloading technique. This vacuum technology reduces the cost and time of the treatment. Next topic is dewatering. Dewatering is nothing but removing the water from the construction site to keep them dry. Dewatering is essential to construct the foundations and other underground utilities where the water table is at shallow depth. Sometimes the trenches may be filled with rainwater in the rainy season, which needs to be removed to continue with the construction work. So the purpose of dewatering during construction stage can provide a drying platform to work, reduce the lateral pressure on the bracings in excavations, increase the strength of soil due to reduction in the pore water pressure, increase the slope stability, prevent the seepage problems such as piping, and also reduce the air pressure in tunneling operations. And the dewatering after the construction reduce or eliminate the uplift pressures on bottom slabs and permit economics from the reduction of slab thickness of basements, buried structures, canal linings, spillways, dry docks, etc. And also they provide dry basements, reduce lateral pressures on retaining structures, control embankment seepage in all dams, and they control seepage and pore pressures beneath pavements, side hill fills and cut slopes. There are 4 important dewatering methods: well point method of dewatering, adductor wells, open sump pumping, and deep well point method. So first one is well point method of dewatering. A series of wells are drilled to the desired depth with the planned spacing. The minimum spacing should be 2 meter. The riser pipes are placed into the wells, and their top ends are connected to a flexible swing pipe. This flexible pipe is connected to a header pipe which will discharge the water to the nearby drainage system. One end of the header pipe is connected to vacuum pump, which creates suction pressure in the wells and draws water. The water then travels from the well points through the flexible swing pipe into the header pipe to the pump. It is then discharged away from the site or to other processes to remove unwanted properties such as contaminants. Next method is adductor wells. This method is almost the same as that of the well point method, but here instead of vacuum pressure, high pressure water is used in the riser pipes. This high pressure water creates a reduction in pressure at the well points, which draws water through the riser pipe. The method uses the Venturi principle, which is the reduction in fluid pressure that results when a high pressure fluid flows through a constricted section of a pipe. Next type is ejector wells. The main advantage with this method is it can lower the water table up to 45 meter deep. Therefore, it can be used for low permeability soils. A single pumping station can be used to operate up to about 75 ejector wells installed in an appropriate array around the works. They are particularly suited to operating in fine soil conditions. Adductor systems are able to extract groundwater and generate a high vacuum at the base of wells up to 50 meter deep and of as little as 50 millimeter diameter. Vacuum drainage can provide dramatic improvement in the stability of silty fine sands and laminated silts and clays by the control of excess pore pressures. The advantages of adductor wells are they are flexible to install and operate, also effective to greater depths, best in low yielding wells. Venturi in base of well creates vacuum. They can be used for inaccessible areas such as railway lines and canals. The next type is open sump pumping method. This is the most common and economical method of dewatering. Here the water is diverted into a sump by gravity. This method can be used in the site where the soil is sand or gravel. If the excavation area is large, multiple sumps are required along the longer side to collect the water, or simply a single long narrow sump can be provided instead of multiple sumps, which is called a ditch. Deep well method of dewatering excavations. This method is similar to well point method, but the wells are much wider than well point method. The diameter of wells are between 150 to 200 millimeter, where it is around 50 millimeter in well point method. The water is allowed to flow towards these wells by gravity. As a result, the groundwater level in the surroundings would decline according to the type and arrangement of pumps. The depths of the wells could reach up to 30 meter. This method is generally adopted when a heavy amount of water from the ground has to be drawn out. So the wells are protected with casings, and a pipe is installed in the borewells to extract the water collected in it through a pump. The boreholes are also protected with well screens to to prevent the sediments enter into the well. It is prudent to assess ground permeability conditions beforehand, since the whole process of accumulation and pumping takes quite a bit of time. This may cause settlement in the nearby areas, and hence a different technique might need to be adopted. Next method is electrokinetic stabilization. One of the most common causes of foundation movement is the volume change of active clays. Electrokinetic stabilization is a technique of applying an electrical current through a soil mass to promote the migration of chemicals from injection points using electrodes. This technique is particularly suited to weak clay soils that require strengthening and yet possess a low hydraulic conductivity, thus preventing the economic introduction of chemical grout using conventional hydraulic means. Electro-osmosis. Electro-osmosis is a phenomenon describing water molecules being dragged along as solvation shell by the protons, which are conducted from anode to cathode. Electro-osmosis has been investigated as a means of dewatering loose soils, clays, and other colloidal materials, including coal washery wastes. It has also been applied to desalination of salty brown coal in the German Democratic Republic. So, when an electrical potential difference is applied across the soil mass, cations and anions are attracted to the cathode and anode respectively, whereas the neutral particles are attracted to neither. The movement of ions within the pore water causes a transfer of momentum to the pore water. The corresponding direction and rate of pore water movement are determined by the net transfer of momentum by both the cations and anions within the pore water. Because of the negatively charged clay particles, the predominant ions with the pore fluid are cationic, and the water therefore moves from the anode to the cathode. The two fundamental factors that control the degree of water migration are the cation to anion distribution within the pore water and the water cation distribution within the soil. So, the advantages of electro-osmosis are: it can be effective in soils with relatively low hydraulic conductivity. Equipment required is not complex and needs minimum surveillance and monitoring. No need for heavy construction, operation and process as with other chemical or mechanical stabilization methods. Depth of stabilization not be a constraint. Recently, a more economical alternative with conductive polymers in geosynthetics called as electrokinetic geosynthetics have been developed, which are corrosion resistant and also has the added advantage of facilitating drainage. This new technology is patented. So this technology has the potential for using as conductive edge drains for dewatering and stabilization of road beds under existing payments.